This is problem 167 from Fundamentals of Structural Mechanics. This is Group 12, Michael Blau and Ryan Herdigan. The problem statement. The beam shown below has a rectangular cross-section of depth 4 and width 2, and has a length of 50 length units. It has a uniform mass density that gives rise to a constant body force of B of x equal to negative 2 E2, force units per length units cubed, and is subjected to a surface traction on its top surface that is bilinear with respect to x2 and x3, defined as x reaching a maximum value of 15, which is force units per length units squared, as shown. Find an expression for the applied tractions, find a resultant applied loads, Q of x and M of x, equivalent to the surface tractions and body forces. Find the distribution of resultant force, capital Qx, and resultant moment, mx, along the beam. Find the displacements and rotations along the beam. For our problem, we're not required to find the displacements and rotations, so that will be ignored for the solution. Next thing to note is the x-axis. The x3 axis that we commonly know in beam theory is referred to as the x-axis. So at the beginning, it will be referred to as x3, but later it will be referred to as the x-axis. But just note that both those terms are synonymous.
Now I'll explain what bilinear means. First, we'll look at the left image, which is looking at the beam in the x2, x3 direction. The distributed loading shown is the max values acting on the beam when x1 is 1. From this observation, we can create a function which is c times x3. Now this c is a constant of the magnitude of the force with respect to the distance on the beam. Now we'll move on to the right side of the image, which is the x2, x1 direction. Again, we can create another function for the loading, which is c times 1 plus x1. Now, it is 1 plus x1 because x1 is taking about the centroid of the beam. And when x1 is negative 1, we get that function to go to 0, which the force is 0 at x1 is equal to negative 1. Now, combining these two equations, we can get an overall equation for the force, which is equal to force equal constant times x3 times 1 plus x1. Now, using the initial conditions, we can get when x3 is equal to 50 and x1 is equal to 1, the force we know will equal 15. Solving for c, we get 0.15. Now that we know what the equation for the traction force on the top, we can actually solve for the overall traction force acting on the system. From the initial conditions and from the problem statement, we know that there is no force acting in the E1 or E3 direction. And the force acting on the top of the beam is acting in the negative E2 direction. Now we'll solve for the applied loading. The equation in red is the definition of the applied loading, or Q of x. Plugging in what we know, we get this following equation for Q of x. We're going to start with the first integration of the body force. Now, we'll work out the integration from negative 2 to 2 first. Next, we'll move on to the integration of dx1, which is from negative 1 to 1. Solving this integration, we get negative 16 E2. Now, we'll move on to the integration of the traction force. We can take out the constant that we know, which is the negative 0.15 x3. With this out, it'll make it a little easier for the integration. Now, we'll integrate dx1 from negative 1 to 1. And from this, we can get that integration to equal 2. Simplifying, we can get the integration of the traction force to be negative 0.3 x3 E2. Combining these two terms, we can get the applied loading equation Q of x to be negative parentheses 16 plus 3/10 x3 in the E2 direction. Now we will find the applied moment, or mx. Again, shown in red at the top of the screen is the definition for the applied moment. Now, I want to point out that there is a p in this equation. This p is the position vector and should not be confused with projection tensor, which we learned earlier in Chapter 1. On page 243, you will find the definition of the position vector. For our case, for the top surface, we have x1, e1 plus 2e2. That 2 for the e2 is because we have to go from the centroid up to the top surface, which is 2 length units away. Also, x1, e1 is because the force varies with x1. And for all the other surfaces, we have the definition of position vector, which is x1, e1 plus e2, or x2, e2. Plugging into the mx equation, we get the following equation using the terms that we already know. Now, simplifying by performing the cross product, we will get this following equation. Take note that I've already taken out the constants in the second integration. Now we can perform the integration of the body force. We'll start with the dx2 part of the equation. Taking the integration from -2 to 2, we get this following mathematical expression. From this, you can find that it will go to 0. So the body force integration for the mx is 0. Now we'll move on to the integration of the traction force. Again, performing the integration from -1 to 1 for dx1, we'll get that following equation. Note that we have changed the 0.15 to fraction form, which is 3/20. This will just make it easier when we combine the two fractions together. Once we do that, we will actually get -1/10 x3 e3. And combining these two terms together, we'll get mx to equal -1/10 x3 e3.
Now we can look at the equilibrium equations that are found on page 247 in the text. The first one being capital Q prime plus Q equals 0. Since we've already found the applied loading, now we can find the resultant force. Moving the Q to the right-hand side of the equation and taking the integration of both sides, we're able to solve for Q. I'm just going through the math here. Now we find that we have a constant, C1, that happens after the integration. Continuing on to simplify the expression, we have this here. This next part, we're using Q of 50 equal to 0 to solve for C1. Now Q at 50, which is along the x-axis or x3 axis, as we talked about earlier in the problem statement, is where the tractions are all equal to 0. So at that point, we know that the equation will be equal to 0. Therefore, we can solve for our C1. And for this case, we get -1175 E2. When we plug that back into the Q equation, we have our resultant force of 16x3 plus 3/20 x3 squared minus 1175, all on the E2 basis. Now we have the other equilibrium equation, which helps us find the resultant moment. We've already found the resultant force and the applied moment, so we can use those to solve for our resultant moment. When we put the everything but m prime on the right side of the equation and integrate on both sides, we can find our resultant moment, or m. Going through this, we have this mathematical expression. The next step simplifies it. Also note that E3 cross E2 gives us negative E1, but the negatives cancel out if you look at the negative right near the integration symbol. Now we continue on, and we also notice that m gives us another constant, C2. This is just like when we were finding the resultant force. This C2, after being simplified, will be solved. This is similar to our resultant force at x equal to 50. Since we don't have any tractions on that area, we're not going to have any moments, so it's equal to 0. Using that equation, we're able to solve for C2, which is equal to 32,500 E1 minus 125 E3. After we place that C2 back into our m equation, we get our final resultant moment equation. Now we have the results from this problem. We have the traction force, we have the applied loading and applied moment, and we also have the resultant force and the resultant moment. And this concludes problem 167.